capsule is all about Unit 1 in mechanics at John Abbott College. So I'm doing these series of videos where I'm explaining basically everything that I learned throughout the semester for in this video. It's Unit 1 of mechanics. There's Unit 1, 2, and 3. The first unit is all about kinematics, so the equations that you learned in high school. We're gonna use them and maybe turn them into a bit harder questions. I don't think it's too much harder. It's just that we're incorporating many concepts together, maybe more equations together, maybe the context is a little bit harder, but I'd say it's just about upgrading it to angular instead of just linear. That's like the biggest difference to kinematics in high school. The second unit, it's not in this video, but will be about torques, yeah. Will be about torques and more of angular, but now in terms of inertias and angular accelerations, although we do see angular acceleration in the first unit. And yeah, mainly torque and pulleys, a lot of pulleys in the second unit. And the third unit is, I'd say maybe one of my favorite, but it's conservational energy. So conservation of energy and momentum. So work and momentum. Work is like the force that is required for basically it's all in joules, but energy that is required to do a certain amount of work, like it says. So it could be movement, it could be impact, it could be impulse. And momentum is, like the word says, the movement is conserved, so the movement will not stop unless acted upon by a net external force, etc. And even if it is like net external force, it will be conserved in a certain case. I'd say mechanics is really, really interesting. We learn a lot of new stuff that we don't in high school, obviously, and I'd say the tests are a lot harder than in high school. Also depends on the teacher you get, but the concept itself is not impossible. I'd maybe say even it's the basics. It's just that we combine lots of stuff into one big question, and the final is like a really big question. It's not one question. The final is like 11, 12 situational problems, which are all really big, and around 20 multiple choice. So starting off with Unit 1, which is where we're gonna stop at for this video. We're gonna start off with gravity because that's what we started the year with. Gravity has the formula G m1 m2 divided by r squared, where r is the distance of the center of the planet to the object. And if you're on the surface of the planet, usually Earth, it could be other planets, it will just be the radius, because the distance from the center of the planet to that person is the radius of the person. Another question could be like a bird flying, and of course the bird flying is not on the surface of Earth, but still the distance from the bird flying to the center of the Earth, we still consider that as the radius of the Earth, because the distance from the sky where the bird is to the surface of the Earth is negligible compared to how immense the Earth's radius is. So we would always use the G m1 m2 over r squared. And I'd say physics is probably my favorite course, so this really excites me to explain them on these videos. But Fg, or I should say the G, the constant of G, on Earth 9.81 meters per second squared. That's a constant we know from high school. Oh, wow. It's a constant we know from high school. And that actually comes from the exact same formula. Now, Fg is the gravitational force, where F equals to ma, if you recall, and m is the mass of the person, and a is the acceleration of the gravity, if it's a human on the Earth that we're talking about, and it's falling, and there's a fallout force. That force actually comes from m of the human divided by r squared. Sorry, no, this is the g. So the g acceleration comes from G, which is big G, which is 6.67 times 10 to the minus 11. Or is it to the times 10 to the time 10? Is it minus? Yeah, it's a minus 11. I should believe in myself. This is the constant that you should memorize. 6.67 times 10 to the minus 11 is a g times the mass of the Earth divided by r squared just gives perfectly 9.81. And that multiplied by the second mass, m2, which is the mass of the object we're talking about, multiplied together gives the formula F equals to ma, where a is 9.81, aka g m1 over m2, this thing. And that concludes mg equals to m of the person times g. So it's not always the same anywhere. This does not apply anywhere. So m times 9.81 does not apply anywhere because the planet could be different. If the planet is different, you have to come back to this equation, or rather at least this one here, so that you give the correct constant of that planet. So the the acceleration of that planet. So since we talked about F equals to ma, actually we're not going to jump into that yet. That's like the second part of unit 1. Now we have two planets that are attracting both towards each other. And this is actually the Newton's third law already. Newton's third law. Any action reaction forces. So this is a force of planet 1 attracted to another, and another force A and force A by B and force B by A, because this is planet A. No, this is planet B, and this is planet A. Oh, no. This is planet A and this is planet B. Sorry, my bad. So this is a force so this is force on A by B. So it's on A felt on A by B. So it's going that way. Force BA, so it's force on B by A. So this force is caused by A and it's felt by B. That's what these FAB or FBA means, and you should understand. You should memorize how these notations are written so that the tests don't confuse you. Are equal magnitude, and they're opposite in directions, but they're equal because the attraction is always, the force of attraction is always this formula. And if you realize, no matter if it's the FG of A or FG of B, that's, well, not gravitational, but it's the attractive force. Let's just say that these forces are FGs. The gravitational attraction forces are both dependent of the masses of each other. But then no matter if you do m1 times m2 or m2 times m1, they're commutative. So they're giving the same thing. It's just that the direction is different. So there's a question that you will definitely get. Definitely, I say 100% get on a test or exam or any sort of other question. There's a planet and there's another planet. One planet is like 5 times smaller than the other one. That's like a fifth the size of this one. So they will ask you which gravitational force is bigger or same, or do you want to know which one's smaller. They're going to be like, oh, A is smaller, B is bigger, C is, well, they're the same, and these, we don't have enough information. You will have to choose, I forgot which one it was, but the one that says that they're equal. They're equal, and it sounds ridiculous. Even a human that is standing on Earth, okay, the force that the Earth exerts on the human and the force that the human exerts on Earth are equal and opposite. Meaning that the attraction force of Earth to the human and the attraction force of the human to the Earth is the same. It's just that they're in the opposite direction. And that could sound insane, especially if you can't grasp it right away. There's a light bulb that's hanging on the pole. There is a gravitational force of the lamp. And there's also action-reaction pair of the gravitational force to the lamp. So the lamp is also pulling on Earth. It's just that it's so negligible in terms of mass, because there's masses here, that this force, you can barely feel it. You can barely feel the Earth being attracted to the lamp, or yourself standing on Earth. You can't really see the Earth approaching you when you fall. Let's say you're falling. you're falling and you're going attracted to the earth, and you're just like moving towards earth. But then earth is actually also having the exact same force, attraction force from the earth towards you, but then it's really because of the mass difference, and basically you falling toward the earth is so much more significant than the earth moving towards you, that we basically just never see it. And like the reality versus actual physics type questions are really tricky, and they are the false predictors of physics, if I know what I'm talking about. Anyway, it looks weird, but that is the case. Anything that is on the planet Earth has action reaction force, which is equal and opposite. So the Earth is also feeling attraction toward the little ball that is falling towards Earth. That's all about gravity. You're gonna have planet, another planet, and you will get coordinates of these planets. The coordinates could be x and y's, and then they tell you the distance between each of them, usually right triangles, and the masses of each. And to be asked, what is the total net gravitational force on planet 3? All you need to do is to find this vector, and add up vectors. To add up vectors, it's vector 1x to the 2 plus vector 2x to the 2 plus vector 3 x component to 2 root it, and or we can just do the trigs. You can find the trigs, but adding vectors should be taught in high school, and finding the theta could help for finding your other components, and then adding up your vectors. So let's like I said, the x components plus the x components added up together, y components plus the y components. So the x component of that guy and x component of that guy, and the y components of this one, so there is no y component here, and the y component of that one. Sum it up and you will have vector form of the polar form of vector, or the component form. Component form is when there's a x and y, and the vector is x and y, or the polar form, the magnitude of the force at a certain degree. So we're going to give a direction. You have to give a direction if they tell you to give a polar form. That's polar, and that's component form and polar form. For finding the force magnitude, like I said, it's this formula, and you just need to plug in the different masses. Appropriate ones don't mix up, and the r is just the distance between the centers of each. And like I said, you can use Pythagoras to find each one of the missing distance if you are missing, which likely you will be missing. So we're gonna be jumping into kinematics. There's like this little portion of gravity that we learned before kinematics, but kinematics is basically positions, velocity, acceleration, and combining them and treating them versus time all the time. And it's really high school review if you are still fresh in mind with your high school stuff. X of t, v of t, L of t, they are the slopes going down. So this one is the slope of x, this one is the slope of v, and going up it's the area. So the area under the velocity time graph is the position time graph. The area under the acceleration time graph is the velocity time graph. And always you can look at the type of graph it is to sort of figure out what is constant and what is changing. So if that was the acceleration, you can know that the acceleration is constant, and that if that's the velocity, you know that the velocity is increasing by a constant rate, which means the slope A is constant. But then if the velocity is changing all the time, the position will have to be a curved or a parabolic function, because the slope of the position time graph will be always changing. So then it's like a curve, and in this case it's increasing all the time. So it's increasing, it's extra increasing, I'd say. Like, now average acceleration, average velocity are two things you should remember, other than the normal velocities and displacement formulas. So average is always delta over delta t, delta x over delta t. These are like common sense, but we kind of mix up sometimes, so just put an emphasis on that. And averages are always useful for example, this one, only when, well, not only when, forget what I said. So basically the area could be a negative or a positive. That's also something you need to know. If it's a positive, you're adding it. If it's a negative, you're taking it away. And there will be questions that are graphical. They're gonna give you like a graph, usually velocity time graph, and go like, oh, what is the instantaneous acceleration right here? You just need to look for the slope right there. And if you're not given some coordinates, you can just look for the slope with like using a ruler and trying to figure out what is the delta y and delta x. That's something I didn't do for one of my exams. Otherwise, just general review of your equations. You don't really have to demonstrate any equations, but v final equals v initial plus at, v final 2 equals to v initial 2 plus 2a delta x or delta y. And we also have delta y equals to vit plus 2a plus at to 2 divided by 2. And I'd say those are all you need to know. There is no other things. You could know that the trapezoid works with the initial velocity and the final velocity being the heights of the trapezoid, and the trapezoid area.
Who are you talking to?
Oh, it's being filmed. And the trapezoid area will be, well, your area under the graph of VT, which is your position time graph. Well, the position time that you're looking for. And that applies to the v final plus v initial divided by 2 equals to delta x over delta t equation. But again, this one is not that much used. It's just geometrically correct. You can turn that into the other this one, this equation here, by using difference of squares. Oh, did I write v initial? Yeah, so there is difference of squares I could use, but I doubt any teacher will go that far. There is like v final minus v initial that you add to it, and then that turns into v2 minus v initial 2, and then that's where this comes from, because if it's negative, you bring it to your sign, becomes positive. There could be some stuff like that. You could play around with the formulas, but it's probably too into details. And kinematics, you will definitely have to understand that when objects fall and they start at the same initial velocity, no matter if they go up so high up or just a little bit high up, when they come down at the same level of y height, this is the height of y, if they went up, if their initial velocity was the same, no matter even going down, no matter the direction, their velocity will always be the same at the same y value. Remember that. So an object being thrown up and falling down, they will have the same speed at, let's say, the 3 meter that they started initially, as long as the velocity is always constant. So one ball is thrown up at 5 meters per second, then it will reach 5 meters per second at 3 meter. If it was 3 meters per second going up, then it will come down at 3 meters per second going down. There will be negative velocities. Another interesting thing is that when they land on the floor, it was the same concept kind of. If they throw at a certain velocity, going up and coming down, and they reach a maximum velocity here, whatever the maximum velocity they end up here will always be the same if they started at the same height with the same velocity, no matter going down or up. So let's say you're throwing a ball downward with 3 meters per second velocity. So it will just fall like that. Versus another ball that went up 3 meters per second, stopped at one point because of gravity, and then came down. They will reach the same maximum velocity. And that is, again, because if 3 meters per second they went up, comes to a stop, and that's the first theory I talk about, that they will reach the same height with the same velocity, just negative, then that means they initialized with the same speed as the first ball, ending up with the same max speed when they land. That's something you definitely need to know for mechanics, in terms of, well, that's like more theory-wise. So definitely get used to using these formulas. If you get used to them, these concepts, like the theoretical concepts of, when an object goes up and comes down, and they have a certain speed, where's the same speed, and what kind of height, you get used to the phenomenal that happens. Of course, observe your answers, not just blindly solve them by just plugging in. I'd always say understanding why something happens in an equation is totally essential when it comes to mechanics. You can do everything component wise. That's something we didn't really touch in high school. So all of the kinematics equation can be broken into components. So it can be the same for a y. So ay. So if there is different acceleration on x and y direction, that could happen. That's basically an alien planet. Then you just apply the same formula to your velocities, but component wise. So velocity in y, velocity in x for both initial and final. And that's the same for other formulas as well. This one. And of course this one as well. You just break them into x and y components. That is totally fair. That's totally doable. And sometimes you will be asked to draw vectors. So I was just asked to draw vectors like this one. Let's say it's a very simple one. F minus equals to at. So then you can do, let's say this is final velocity vector, and that's initial velocity vector. If you want to find the at vector, well then that's v final minus v initial. That's plus v initial. Take away v initial will be like this. So the acceleration vector will look like that. And the acceleration vector will be the change in both of them. So we could just try like this. Either way, these expressions formula-wise can be turned into vectors, and yeah, that's about it. And the other new notation I didn't see myself in high school is the R. And the R is the same thing as displacement vector, like the xt or the pt that you see. But the R, instead of writing x every time, it's basically the change in velocity. And that is because of the notation. It's just mixing up notation. When there is a movement, there is a change in position, let's say in x that way, and then y that way. So then there is a delta rx over here and delta ry over there. So then that's like the total delta r. Delta r just basically means change in the positions. And the change in position, I said, will be the velocity, not because it literally means that, but let's say this is the first displacement, and that's the second displacement, meaning that's like the first triangle, and then another second triangle, and each of them is like a delta r. This is delta r, that's a delta r. Well, then what we have is the initial and the final position. And the initial and final position could find the average velocity direction. And that comes from the equations as well. But if you have, let's see, just use another color. This one here, this vector here, from basically position 1 to position 2, this will become the average velocity vector. So points in the direction of the delta r. I should have said r1 actually. r1, r2, r2 here. Oh my god, that's invisible. r2, and that will be the delta r, which basically is the same direction as the average. There isn't too much you need to know about this. It's just that there is different notations using r instead of velocities. Otherwise, it's just all the same. So velocity equals to initial velocity plus at, and like the vectors that we could draw out of these ones, we can also draw other types of vectors. Vector finals equal to vector initial plus delta v. This one can be also drawn such as in that case this is velocity 1, let's say, and that's the change in velocity. So then that's the final velocity. Again, it's very simple, but it makes total sense. If that was the initial velocity and the change was pointing that way, this vector will be changed accordingly to this vector over here. So naturally, it should look something a bit higher and a bit longer. No, go that way. That's all there is for the notation one. And that delta A in here is now going to be A average. It's the acceleration vector. So the change in position vector will become the velocity, or average velocity. The change in velocity vector will become the average acceleration vector. Those are the stuff about vectors you should know. Now we're going to go into circular motion. Circular motion is a big part in mechanics, and it's new, so if you don't listen properly, it might sound confusing just because it's new. There is 3 things: centripetal acceleration, tangential acceleration, and the total acceleration. And I'm talking about acceleration because otherwise the movement just looks like a circle. There's nothing hard about the movement. It's just going circle motions, circular motion. But if it is in a constant speed, if the speed is constant, then there's only one type of acceleration. Yes, there is acceleration, even if the speed is the same, the speed of it spinning is the same. It's called the centripetal acceleration. Let's say that I write properly for once. There. Centripetal acceleration, AC, is equal to v to the 2 over r, but it's just acceleration that is changing direction. It is changing the direction of the velocity. And that matters because else it will not be spinning. If it's spinning, if it's turning, the motion is always changed. The vector of the velocity vector is constantly changing. If it is changing, there must be acceleration. Acceleration doesn't mean it has to be speeding up or speeding down. Deceleration and acceleration basically is the same thing. In English, we always use the word acceleration. But it could also be changing direction. That is an acceleration because the velocity vector still is changing. Remember that the definition of acceleration is just change of velocity. Direction-wise, that works as well. And that is just the tangential velocity squared divided by the radius. That's really handy, and you should totally memorize it, not just have it on your equation sheet, because the tests are really tight packed and you don't really have time to think about it. You should just have it in the tips of your fingers. And many things will be looking like this, where there are discs or spinning motions, and there's a 2r, there's a 2r radius, there's a r radius, so some radiuses are bigger, and there is the velocity that are some bigger, some smaller. And you will be asked which has the biggest, or just put them in the increasing order of the centripetal acceleration. All you need to do is just plug in the numbers. Plug in your algebraic expression into this one and see which one has the bigger coefficient of fractions. And I'd say that whatever that is squared usually is dominant. In this case, the velocity is squared, so velocity is dominant. So if you see a very big velocity, you should always calculate it though. So for example, here's just v to the r, v squared to the r. Here will be v square. Well, it's not actually calculated. It's not actually balancing right now, but let's say this is a normal v. This is a 2v. That's a v. V square over. It's just 2r. Yeah. And this one 2v square. So 4v square over 2r. That can cancel out to 2v2, and so on and so forth. So then you can, this one's 4v square. You would just compare the coefficients using your calculations, and they'll always be algebraic. Something that I was kind of stuck about is the skateboard park. So the skateboard park is a non-uniform acceleration, and here this was a circular motion, but a uniform one. Uniform meaning that the spin was constant speed, so then there's no tangential acceleration because the speed of it turning is the same. But if the speed of it turning is not the same, such as a skateboard going up and going down, so the speed of going up decreases as it goes up and increases as it goes down, and decreases as it goes up again, and then decreases as it goes down again. So then in this case, the acceleration, it's not only the centripetal acceleration that keeps it rotating, which is changing the direction. It's not only centripetal acceleration. There's also something called a tangential acceleration. Tangential acceleration, AT, is equal to alpha r, also something you should memorize. And alpha is, we'll talk about in circular, but the change, the acceleration of an angular velocity, omega. Omega is basically like a delta. No, it's like a velocity v, but in angular form. That's what omega is about. So alpha is basically the acceleration, like a that we know, but in angular form. Okay, so it's like a speed up of the circle. It could be a circular motion. It could be a ball spinning and just spins faster and faster and faster and faster. So the rate that it is changing, so the rate of the speed changing, rate of it accelerating is the a, not the rate of accelerating. The rate of velocity speeding up is acceleration. And one thing to know, one concept you just need to understand all of this is that acentripetal will be always pointed toward the center, first off. And tangential velocity, depending on whether it's speeding up or down, will be pointing towards or opposing the motion. If it's going that way, that's velocity, or if you want to say that this is the omega. If it is going this way and it's speeding up, obviously a tangential will have to be helping it, so also going that way. But if it is slowing down, if it's going that way and it's slowing down, now a tangential has to be pointing the other way. So vector-wise, it will be pointing that way instead of this blue one here. Instead of this blue one here, it will be pointing that way. And what that changes is the total acceleration. Total acceleration is the vector sum of the centripetal and the tangential acceleration. Vector sum is basically Pythagoras. That. But instead you do a centripetal to the 2 plus a tangential to the 2 square root. And remember that AC is v2 over r, and that v is basically the same v that we're using for calculating a tangential. So A tangential, basically think of it as A. In terms of V that we have, V is like the instantaneous linear speed. So we're always playing between linear speed, linear acceleration, linear everything, and angular speed and angular acceleration, angular everything. So we can talk about the angular rotational parameters here. But V basically is omega, but there is a relationship between them, and it's called omega r. R is the radius. No surprise, A tangential equals to alpha r as well. And who'd have thought S, which is the displacement of the arc, basically this displacement, like the distance linear wise distance, like basically like delta x, or if you roll a ball on the ground, it's just gonna keep rolling, right? It's gonna roll, and how many meters it did roll is basically the segment of how far it traveled on the circle. Will be a S, which is delta r. Well, no, delta theta r. Theta means the amount of angle that it traveled, so it looks like that. So that's the change in radius, change in angle, and everything's multiplied by its radius times its radius times its radius times its radius. And we can play with these to get centripetal acceleration, because velocity, we know that velocity equals to omega r, so velocity square will be omega square r square, so v square can be substituted with omega square r square divided by r. Oh, you see that it cancels out, so a centripetal also equals to omega r square times r, and a total, you can find it from there as well using a centripetal and a tangential, where a tangential, like I said, is this one and could be found from the kinematics as well. So kinematics works really well because it applies as much to the linear than to the rotational, and it works as long as one thing is constant, called the acceleration, or the acceleration. If the acceleration is constant, these kinematics equations work. So instead of velocity over tangential, well, a normal a that we use alpha instead, and we can do omega final equals to omega initial plus t, and omega final to 2 equals to omega initial to 2 plus 2 alpha delta theta. And same concept. You could be asked that it will start rotating at how much ever omega speed, and it will increase to a final speed of blah, and ask for the alpha. Or they will give you the radius, they will give you the tangential speed, tangential acceleration, they will give you the total acceleration, and ask for centripetal acceleration, etc. So it's just really playing with algebra. The concept is basically all this. There's nothing more than this. That's pretty much it. It's really not too hard. Now gears and pulleys. Gears and pulleys is something that you should definitely understand physically, not just do practice questions. If there's a pulley, everything that's tangential is the same. That sounds kind of ridiculous, right? It's obvious, but everything in physics kind of become not obvious once it turns into numbers and formulas. And if it's a gear, anything that is angular is the same. Angular, by angular I mean how much this guy turns in terms of angle is equal to the distance, well, the displacement, angular displacement of this disk. And that's because if this one rotates, this one has to rotate. How much this rotate is equal to how much this one has to rotate. And so everything that has to do with your delta theta, your omega and your alpha has to be equal to each other. Well, they will have the same angular acceleration, have the same angular velocity, and same displacement angular. These are all linear. They will not have the same angular stuff. How much this guy moves angular has nothing to do with how much this little one does. Well, it has something to do, but it's with the relationship with the linear one. The linear one has direct relationship. Because how much this one moves in linear, like meaning the instant point at the rim, how much it moves has to be equal to how much it moves on the rim over here, no matter if it's smaller. It just moves faster. So then we have the same V, the same A, the normal tangential A that we know from long ago, and the S, or if you like to say delta X, are the same. And these, again, can all be found from the kinematics equations. All of these equations. There could be a question going like, oh, the initial angular velocity of this guy is 3 radians per second. And the final is 1 radian per second. And it was done in 0.5 seconds. Find the tangential acceleration of this A. How to do that? We could first find for alpha, which is the same in both. So they have the same alpha, but different A tangential. But remember that alpha is related to A tangential by just the radius, because A tangential is equal to alpha r. Just need to divide it by its individual r, because yes, they do have different r's. They have different radius. You just need to play with these relationships. Similarly here, if you have they will tell you the initial angular velocity, final angular velocity. They will even maybe give you the tangential acceleration, and I should say maybe alpha. They will ask you how much they displaced, how much did this pulley, how much linear displacement did the little pulley do. Well, you have to realize that it's the same as the first one, so you don't even need to bother thinking about it in this case, if that was the question. Else, if they were asking for, let's say, angular stuff over here, the angular stuff was the big one, has nothing to do with the angular stuff over here, because it's only linearly identical, or it's not identical, but they're separating, their relationship is only linear wise, not angular wise. But you could again use your really powerful radius, each have its own radius, and just need to apply one of these rules to find out each other. So that's actually all for the first term, the first unit. So the second unit will be about forces, free body diagrams, and net forces, accelerations, and torques.